Greetings, pre-calculus students. Um, Today I've got a lesson for you, part 2 of the trig identities and proofs. This time, rather than just going mostly with just simplifying down expressions and seeing what it equals, we're going to focus more on the proofs, kind of like you did in the Alex for like problems like 3 and 4, or I'm sorry, 4 and 5. So we're going to work more with actually proving that something is equal. And with the whole working online and security online, I found this protecting yourself from identity theft a little amusing, so I'm sharing that with you. Enjoy. Um, so some basic stuff I'm gonna give you here. It is by no means like a follow these steps and everything is good. It's just some guidelines of things that I have encountered over my many years of doing these things that have served me well, and I hope will do the same for you. First and foremost, you've got to know those identities. I've told you, have them written down so you can refer to them. That's definitely a plus. But the sooner you can kind of even wean your way off of those and not have to look at the paper and you just know the identities, you're going to be a lot better off. You'll be a lot more fluid with these. You'll work a lot faster and more efficiently. You'll be a lot happier with them. So learn those identities. Keep them committed to memory as you can. Typically in these, you'll have two sides of an equation. Take the uglier side and try to simplify it rather than trying to take something easy and make it difficult. You'll find that, or at least I found that pretty helpful. Third thing, work on one side of the equation and get it to equal to the other side. That's generally what I do. It's kind of the mathematical purist approach, but technically there is nothing wrong with like working on one side and then working on the other side and then trying to get them to kind of meet in the middle and equal the same thing. It's not my cup of tea, but it is a valid excuse me, form of proof. Number 4, we've done a lot of, again, dealing with cosecants and stuff, and cotangents and secants is a pain. Typically when you write stuff in terms of sine and cosine, things work out for the best. If you can even write it in terms of just one function, all cosines, all sines, all the power to you. That's pretty cool. Use algebraic techniques you've learned in other courses, so like simplifying expressions, combining like terms, foiling, factoring, distributing, common denominators, canceling, multiplying by conjugates, all that kind of deal. If it's legal in your algebra class, it can fly here too, with a couple of exceptions that I'm going to share with you in the video here that comes up later in the problems. Sometimes it may be helpful to multiply quantities by 1 in a useful way. Okay, we've done that before where like to get common denominators, you might multiply one expression by like cosine over cosine. What I'm referring to here is more of, let's say I have like a 1 plus cosine in the denominator. I know that's not an identity, but if I multiply it by its conjugate 1 minus cosine, then it becomes 1 minus cosine squared, which is a Pythagorean identity, and you can use it. So that kind of enables you to manufacture a Pythagorean identity where one wasn't at first. And lastly, don't give up. Try something. Even if what you're doing crashes and burns and you get stuck and don't know where to go from there, it may lead you to, a good place to where you can figure something else out. So stay diligent and try not to get frustrated. Okay, we'll start basically here. Again, when you're doing these things, this is one kind of a little warm-up or review from your last lesson. It's a simplification type of a thing. While you are certainly welcome to, distribute the cosecant into there and the cotangent into there, and then write stuff as sines and cosines and kind of do your thing, it works just fine. I'm sure you can make that work as well. So I'm going to do it a different way. I'm going to actually start off writing stuff as sines and cosines. So I'm going to write the cosecant as 1 over sine. I'm going to write the cotangent as cosine over sine, and then leave the 1 minus cosine alone. Again, this is only one method to solve. It is not the only one. I would be quite sure if you did the distribution and then worked from there, you'd get the same answer I'm about to get, so it's no big deal. Why did I choose this way? Well, I just know that when I do a cosecant and a cotangent, it's going to give me a sign on the bottom in both cases, which gives me a common denominator, which is cool, because then I can take this common denominator of sine and then write my 1 plus cosine as 1 fraction. Okay, so what does that do for me? Well, again, I'm going to write the 1 minus cosine. I'm going to put that over 1, so I take top times top, bottom times bottom. So on top, when I distribute the 1 times the 1 times the negative cosine, cosine times 1 and cosine times negative cosine, I get this thing on top. On bottom, sine times 1 is sine. This is an example of where I was talking about, like if you multiply by the conjugates, good things can happen. You can basically manufacture an identity. Now, granted, this is not actually multiplying by 1, where I did the same thing to the top and bottom. That'll come later. So those two cosine x's, one positive, one negative, cancel. So I'm left with 1 minus cosine squared on the top. Hopefully by now, after last week, you've learned that 1 minus cosine squared is a Pythagorean identity for the sine squared. And so 1 minus cosine squared is sine squared. They both have a sine on there, so I divide top and bottom by sine, and I get just sine. And if I go back and check, yeah, this wasn't a solve, this was just a simplification. That looks a whole lot simpler than what I started with, so I'll call that a win. Okay, next one is a proof. It's not what does this equal or what does this equal. You either make this left side equal to the right side or the right equal to the left, whichever you prefer. Again, I'm pretty sure I can solve both of these. Like, I can do it either way. I can work on the right side or work on the left side and eventually make it work. Again, I've got a whole lot more practice with these than you do, but typically I want to just take a look, and whichever one either jumps out at me as just looking nastier than the other side, I'm going to work on that. Or specifically, I see a 1 here and a negative sine squared there. I know I can manufacture an identity out of this, so I'm going to play with that left side and just leave this right side alone. Cosine and tangent, that's going to stay, and hopefully somehow this makes that. So what did I do first? Well, I took this positive sine and this negative sine squared, and I switched their order. Okay, first, how can I do that? It is called the commutative property of addition. 3 plus 5, 5 plus 3. It doesn't matter what comes first, just so long as the sign follows. You see how, like, this sine squared has a negative sign in front, so that had to come with it, and then the sine x was positive, so that enables me to use 1 minus sine squared as an identity, and specifically, that is the identity for cosine squared of x. So 1 minus sine squared is a Pythagorean identity for cosine squared. And then plus sine over cosine. Now's where I kind of take a look at, okay, here's where I'm at now. What do I want to get to? Well, first thing I see is I notice a tangent here. And I know I have a quotient identity that tangent is sine over cosine, and I see that I have that. And then cosine, well, if I take a cosine squared and divide it by a cosine, I'll get that too. So basically what I need to do is to separate this 1 fraction into 2 fractions. And can I do it? Yeah, it's like if I have 3 plus 5 all over 9, that's the same as 3 over 9 plus 5 over 9. So I separate it as 2 fractions. I cancel a cosine out of the first fraction. That leaves me with just a cosine. And then my quotient identity says sine over cosine is tangent, which is exactly what we're trying to prove. So that one is done. Okay, number 3. This is one of those cases where something you may be used to doing in algebra is a real bad idea. Like, well, I'm gonna even go back to one of the last ones here. Like some of you might say, well, can I like subtract a tangent from both sides? The answer to that is no. You cannot move something from one side over to the other. That is a big no-no. You might say, well, I can do that in algebra. Here's the difference. In algebra, like you can add 5 to both sides or subtract 7 from both sides, whatever you might need to do, because in algebra, we know that they are equal. In these proofs, we don't know that this side equals that side. That's what we're trying to show. So I cannot use a property of equality in something where I don't know that they're equal. You see, a lot of people will look at this and say, ooh, look, it's a proportion. Fraction equals fraction. So you cross multiply and say, well, this is easy. Yeah, that's also really incorrect because you can't do that. Again, cross multiplication is a property of equality. That works well if you know two things are equal. We don't. We are trying to prove that the left side is equal to the right side. So you cannot cross multiply here because we have not yet proven these things to be equal. We suspect that they are, we don't know. This is one of those problems where, again, you can work on left side or right side. It doesn't matter. I can get the same answer either way, but I'm going to work on the left side here. I think it's a little easier. And I'm going to use that technique where I talked about earlier, where I said to multiply by 1 in a useful way. So again, that's my little warning about not cross multiplying and the why you can't. So don't do that. That's really, really bad mathematics and it will cost you. So I'm going to take this left side and work on it. And I'm going to multiply it by 1. Only I'm going to write 1 as 1 minus cosine over 1 minus cosine. So your first question, is it legal to do that? Sure it is, because I'm just multiplying by 1. Whenever the top and the bottom are the same, it's 1. And multiplying by 1 doesn't change anything. So why did I choose to write 1 in that way? Well, because what I know is if I take 1 plus cosine and multiply it by 1 minus cosine, like that, what's going to happen is on the bottom, I'm going to get 1 minus cosine squared. See, whenever I multiply by conjugates, the inner terms cancel. So the cosine and the negative cosine both cancel. That's where I was talking about, you actually manufacture an identity. So by doing this to this new denominator, I actually made an identity where 1 didn't exist. Now, I think it was problem 16 that I did on the Flipgrid video for you guys last week, where I told you, or it was on one of the problems I did in a video maybe, I told you to, if you messed with the top, leave the bottom alone. Well, this is the opposite. Since we goofed with the bottom, I'm just going to leave the top alone. I know you're tempted to distribute. Don't. Work with just 1, and then maybe we'll mess with the top later on it if we need to, but I don't think we're going to need to. I think something's going to cancel if I just work with 1. And again, we've manufactured this identity, 1 minus cosine squared, which is just another way to say sine squared. This sine squared cancels with one of those signs, leaving me with 1 minus cosine all over sine, which is exactly what we're trying to prove that the left side was equal to right here. So that problem is done. Again, all I did, multiply by 1 in a useful way, in a way that makes the conjugate so I can kind of manufacture an identity. It's kind of a cool little technique. I kind of like it. Okay, number 4, I'm going to go out on a limb here and say that I think the left side's the nasty side. Just going out and just taking a ballpark guess at it, it looks uglier. So again, if you want to write this as like 1 over cosine, and play with it and do your thing like that, works fine. This time, I'm going to actually just go ahead and distribute. Why? Why not? It just sounds like fun to me. You'll see. But certainly you could do it the other way and you'd be fine. So I distribute secant times secant. I get secant squared. Secant times a negative cosine gives me minus secant cosine. So why did I choose this method? Well, because I know that when I take the secant times the cosine, I know that secant is the reciprocal of the cosine, so I can write this secant as 1 over the cosine. Well, what does that do? Well, these two cosines cancel, leaving me with just secant squared minus 1. And I know that secant squared minus 1 not only is a Pythagorean identity, it's actually a Pythagorean identity for what I'm trying to prove here on the right side. So that actually equals the tangent squared. And number 4 is done pretty easily. Whereas maybe if you wrote it in terms of sines and cosines at the beginning, it may have been a little longer, but you could have still gotten here using that technique as well. So there is some flexibility in how you solve. Okay, number 5. Tangent plus cotangent equals cosecant times secant. Again, you say, well, both sides look nasty. Where do I even start? Well, you could start on either side, but I'm going to tell you one of those little tidbits of wisdom or whatever it is that I have in my head, whether it's wise or not. I'm going to share one of those with you. What I've learned over the years is that it's a lot easier to turn addition into multiplication than it is to turn multiplication into division. You say, well, how does that work? Well, it works by if I take this and turn them into sine over cosine, and this is cosine over sine, and just do the whole common denominator thing, it'll turn into multiplication very nicely for me. Now, could I have worked it this other way? Sure, I could have. It might have been a little more painful. Maybe it's something you'd see easier, but that's just kind of what I've seen, is it's easier to turn addition into multiplication, but have a blast if you want to try the other side. So again, these do not have common denominators, so we make them have common denominators. So I take this first, sine over cosine, multiply it by sine over sine, take the cosine over sine, multiply it by cosine over cosine, giving me this as my common denominator, sine times cosine, sine times cosine. Again, this is going to be a situation where I mess with the top and leave the bottom alone. Some of you probably already see where this is headed. Remember my love note that sine squared plus cosine squared is 1. And then if I take 1 over sine and over cosine, you see right where that's leading. But if not, bear with me. So again, I have common denominators, so I'm going to turn it into one fraction. Again, I'm going to use my love note. Sine squared plus cosine squared is 1. And then I can actually separate this by saying that's 1 over sine times 1 over cosine, which is the cosecant, times the secant. And again, we're done. Not too hard. We're going to do 2 more here. And again, typically it is easier to turn addition and subtraction into multiply or divide, so I'm going to do just that. I'm going to turn this cosecant into 1 over sine, and I'm going to leave this sine alone. Now, in the last problem, we added and we got common denominators, so you say, well, this sine doesn't have a bottom. Well, it really does. It's like saying the sine over 1, so what I'm going to do is I'm going to take this 1 over sine and leave it, and this sine of theta I'm going to multiply by sine over sine, which is really 1 in a useful way, to make this have the same denominator as that. So again, I'm not doing anything with the left side. I'm just bringing it down as is, not touching it, not moving it, just letting it be. Just playing with this right side. So that's going to give me 1 over sine minus, and then sine, or sine over 1 times this, will be sine squared over sine. Something like that. Then from there, we have our common denominator, so I put it together. as one fraction. That gives me 1 minus sine squared over sine. Okay, still good. And I know that 1 minus sine squared is really cosine squared over sine. You say, okay, but how is that giving me this thing on the left? What can I do? Well, I can do a couple of things. I'm going to kind of separate this fraction. First thing I'm going to do is say, well, I have a cosine squared on top, so that's really cosine times cosine. And then the bottom I have a sine, which is really sine times 1. So what did that do for me, this separating the cosines like that? Well, it gave me a cosine over sine, which I know is an identity. Specifically, it is one of the quotient identities for cotangent, which we need. So that's kind of handy. And then, whoa, hang on just a second here. That left me with a cosine here. And cosine over 1, remember that cosine is really the reciprocal of the secant. So this cosine can be written as 1 over the secant. And then cotangent times 1 over the secant is cotangent over secant. And we're done that way too. A little bit of creativity involved there, but it works. And last one. Okay, this one's just a mess. So I got this nasty fraction here on the left. I got this thing, and say, well, both sides look awful. I'm going to go ahead and do that little trick I showed you earlier where you multiply by 1 in a useful way, where I multiply by the conjugate of this bottom and kind of manufacture myself an identity. Okay, you say, okay, how do I see that? How do I know that? Well, it's just a technique where you look at something, you say, I got no idea where to go, and I see like a 1 plus sine or a 1 plus cosine. I know that's a technique at my disposal. And secondly, what I know is when I actually do distribute these, again, since I'm going to mess with the bottom, I'm just going to leave the top alone. I know that gives me 1 minus cosine squared, which on our next step I know is sine squared, and then sine squared on the bottom is really the reciprocal of the cosecant squared. So I see where this is headed. So again, this is just a benefit of having done a whole ton of these in my time as a teacher. So again, on the bottom, after I distribute this out, I'm left with 1 minus cosine squared, which is an identity for sine squared, which is where we'll go in our next step. And then the top I just let be. Or in this case, I guess I foiled it. I'm not sure why I did that, but I took secant times 1 and secant times cosine, negative cosine. We'll see why I did that. I got a feeling that was a bad idea. So now I know why I did this. So it was basically working towards the end here. So I knew let me go back. I knew that what I need is a secant minus 1. So if I distribute here, it gives me a secant. And then if I distribute here, the secant times the cosine, basically the reciprocals gives me the 1. So, okay. So this is one of those very few times where I did mess with the top. But if I would have gotten to this step and left it unfactored, you said, well, hell, nothing would have canceled. That would have told you to mess with the top. So where do I go from here? Well, I'm going to write this secant as 1 over cosine, and it'll cancel very nicely with this other cosine. I'm going to write the sine as the reciprocal of the cosecant. Again, normally I do that the other way. I write cosecants as sines, but I'm going the other way this time because that's what my final answer has. So again, these will cancel. So that gives me a secant minus 1, and then basically all over 1 minus the 1 over the cosecant squared right here. And then I just copy, change, and flip, or multiply by the reciprocal if you prefer to say that. So instead of dividing by 1 over cosecant squared, I multiply by cosecant squared over 1, which gives me what I started with, and we are done. So again, I hope this helps. I will have the assignment posted as well online during our online meeting, our virtual meeting this week. We'll go over any questions you had either on this video or on your homework. So see you later, and I hope this helps. Bye.